we can move on to the more general round of discussion. And I would, like yesterday, ask all the speakers from today and yesterday to, come back on screen so that people can see you and us. And okay, Schumit, you maybe want to comment on that and open the discussion.
Well, I just wanted to add to that people have actually determined temperatures from profiles. So there's a paper by Raut and Werner, I think 2019 or maybe even 2020, where they did just that. They actually looked at the profiles and used that to get temperatures rather than timescales.
Well, yeah, it'd be super cool if we could do something like this, but I'm always a bit hesitant, certainly with magmatic systems where, temperatures are changing so much and, there's so much complexity. So there would be always some kind of simplistic assumptions associated with those, but I don't know, maybe, it could be really useful if it works.
Yeah, it worked well in that case, that one example which they had. Yeah. I think they used sanidines.
So what would be the, oh, wait, Dan is here. Dan, just come on, I'll unmute yourself.
Oh, okay. I was just going to say, we've used all sorts of quirks of diffusion over the years to estimate all sorts of fun things. So if more elements you use, you can actually solve an extra intensive parameter each time you do that, in theory. I would say that there is a bit of a question about how one does that. So I had a go at that during my PhD, and I've published a slightly obscure paper in Contributions in Min and Pet on this, where we were trying to run, say, strontium profile against a barium profile. And you take the barium profile, which is usually steeper because it's a slower diffusing profile, and you run it forwards in time until it matches up most closely with, say, the strontium profile. And you can actually then work out both how much time it had to decouple. That's one way you can use it. If you then have a third element, you can actually independently solve for the temperature at which that would actually be a unique solution. So there are quirky methods you can use. It replaces the initial state assumption. In fact, we don't care what the initial profile was in that kind of situation because we're only doing forward modeling from our data. But we are assuming that at some point in the past, when the crystal grew, the barium and the strontium profiles were effectively proportionate. So they're related by a partition coefficient. So there are fun methods you can use where you mess about a bit with what you're trying to get out of these things, but we end up replacing one initial state assumption with another one, which may or may not be valid, which is a slight quirk. The other thing, to return to that idea of using it for temperatures, we actually used titanium in quartz in the Ballachulish Oriole as a thermometer. So it started out as a fourth year project, and we kind of ran a variety of different titanium and quartz parameterizations, and we ended up finding a diffusion situation where the diffusivity of titanium and quartz could actually be used to turn this around. We had nice diffusion profiles, but we could actually use it as a thermometer with actually really very good precision, purely because of that extreme temperature dependence of diffusivity. So there's some fun ones that you can do with strange models.
Maybe coming back to Claire's question from yesterday, today with a little bit more focus on thermochronology and igneous systems. What are the big challenges? What are the big next steps where we need to go?
I think one thing that's really potentially exciting is the fact that a lot of these, so things like MELTs or like thermodynamic software is now moving towards being like a Python-based open source thing. And so now it's now possible to start incorporating different types of software together. So it basically allows us now to I guess, yeah, incorporate maybe uncertainties in like the thermodynamic models, or look at different crystallization pathways, or how changing the composition of, I don't know, the melt within its uncertainties can affect things. So usually, I guess, melt is currently like a GUI that people would have to run manually like 100 times, which is, you know, now potentially you can just do that with like the click of a button. So it really kind of opens up a lot more in terms of exploring the effects of magma dynamics and that kind of thing.
I think certainly in terms of the metamorphic and sort of geochronology side of things, is that the diffusion parameters now are the biggest uncertainty compared to the analytical uncertainties. So when we're trying to sort of fit data to models or assess data against models, actually the diffusion parameter uncertainties are so big that it's just this, you lose a lot of stuff in the detail. So if we're trying to figure out whether diffusion, for example, of argon in muscovite is the most important reason why argon ages in muscovite tend to be younger than uranium lead ages in zircon in the same rock, then we need to know our diffusion parameters better so that we can start looking at whether it's diffusion or deformation or recrystallization or any of these other processes that are operating. So that'd be my big one. More experiments.
Yeah.
But they're really hard to do, which is why people haven't done them.
Yeah, and the thing is, we're getting more and more into details, and this makes an awful lot of experiments that we need to do, right? So Bruce had another question.
Yeah, this was just to broaden up into the more general discussion and draw on what we were looking at yesterday. But I just comment that we've got a lot of detail today about how we're using diffusion data to get at temperature, to get at time. But obviously, one of the basic questions we started off with is how much material moves around in the crust? How does it move? When does it move? And I just wonder what people think the most promising ways forward are going to be to decide the contribution of diffusion as opposed to advection towards mass transfer, because as Roy pointed out yesterday, potentially actually diffusion distances can be really quite big in rocks, and we tend to assume that they're almost nothing. But I just wonder, can we go back to the very basics and say, well, what's diffusion doing about moving stuff around? Someone's got to pick that up and run with it now.
Well, the one thing I'll add to that is that you can actually also model. So if you have a vein, and so people have done that with mantle things, I think. If you have a vein and things are reacting in the wall rock, so you can, I mean, the process is one of fluid flow and reaction and precipitation and all of that. But overall, you can model that also as a diffusion process. And I think there was a paper by Horst Marshall and Ralph Doman and others. They looked at some metasomatic veins in Greece or something, and they did a little bit of that. And I think there's a lot more one can do in that direction.
Yeah, I mean, one of the things you find in those studies is that your processes seem to happen very quickly, and yet geologically, you've got an enormous time span in which you've got potential for things to happen. Mm-hmm. So is it telling us things about episodicity, periodicity in geological processes that we really don't know about, because we tend to take this very average view of the geological past, and things happen over long time periods bracketed by age dates where we have them.
Yeah, absolutely. I've been talking about the fact that you have a pulses play a big role, and I think one such vein forms over a very short time, but you may have a geologically extended period where such veins are forming in a region. And you need to sort of separate those two things out.
I would even go further and say you can extend this to melt transport in the crust, right? Where we do see that we have these melt pathways which create the reaction fronts that we can investigate using the diffusion profiles that we see in the country rocks. So I think there's a high potential to go on the larger scale. So I just want to make people aware that there are some discussions on the potentials of micro CT in the chat going on. So it's a little bit off topic on the discussion at the moment, but people interested in the potentials are referred to Matt's comments in the chat box, please. Coming back to the more general discussions, more points that we need to pay attention to. Tinka.
I do really wonder when I see all the speakers here today with very different backgrounds, different stages in their career, that have been working for ages on diffusion or for a short time, with sometimes working in diffusion or on others. How can we guarantee that new students or new researchers are actually using the state of the art, which is so, right? It's so complicated. There are so many things going up. How can we guarantee that there is an awareness for all these different important little bits that they are brought together?
I think events like this are a first step towards it, right?
Yep,
Is there a checklist? Should
Petrology.
there be a checklist?
Yeah.
Petrology is first, number one. Both Dan mentioned that, I mentioned that. Schubert agrees. The answer's in your rock. Look at it down a microscope. Then after that, doesn't matter.
But there's an awful lot of good sense there, which is that we all have different methods of processing uncertainty, for example. So I have in some way or other incorporated covariance between Q and H, or Q and D naught, for years, gradually improving it all the time. But obviously the people who tend to see that are my collaborators and the sort of my PhD students. So I think even simple discussions like how we measure uncertainty and how we deal with uncertainty, I think we have to make those a bit more public, because they're not usually the shiniest subjects to talk about. Everybody wants to talk about the timescale data. They don't want to talk about the error propagation. It's definitely something we need to actually discuss more among ourselves and have a kind of community space to do that.
Having an understanding what the biggest uncertainty in every problem is. Is it geological uncertainty? Is it
It's a research.
which bits of our data? Is it analytical?
I think it's a human error, the
Yeah.
misjudgment of something.
Assumption error.
Yeah.
Well, I
So,
guess that's meeting
Lucy,
like this one. Sorry.
I just wanted to mention that Lucy suggested that we should make sure that we have research-oriented teaching and critical thinking as part of our programs. Things that are critically important for the diffusion modeling that we do.
Yeah, I just meant that simply implement to the lectures what we do.
Add on to that, Thomas. I think.
Can't hear you.
So yeah, Lucy, are you done? So
Can
Roy,
you hear me?
You wanted? Yes.
No, I just wanted to say that it's. I think that it's as easy as that we just enthusiastically implement what we do, the really the advances which we have now into the lectures. And I think that what is the most important thing is that the students are aware of the uncertainties, because they usually blindly believe everything what you give them. And they should be able to think about the results critically, and there are many ways how to bring it to them, how to let them think.
Yeah.
And it's also more
So first
attractive.
Chiara and then Roy, please.
Yeah.
I just want to say that meeting like these might really help, because yes, I mean, teaching is fundamental. but also at certain level, maybe having a focus meeting like this really, really helpful. And then the idea of having a more sort of community working together instead of trying to do their own things and share, a bit of sharing, more sharing of our result and also failure.
Roy, you wanted to say something.
Yeah, I was just going to say that the most inspiring thing is showing progress, and you know, there've been, and every talk at this meeting has done that. It's shown that there's been progress on various different aspects of diffusion, and that's what makes the subject interesting, I think, because it's alive.
I had something.
Yeah.
Okay. What Chiara said, I think, is really important, as well as everybody else kind of like said about like uncertainties and failures. And I think really important is methods. So a lot of our papers are often like brushing over methods. And I know it's maybe not the right place to like, you know, write a 2-page detailed analytical thing in your actual paper, but I think we have to have something like that in supplementary data, because Sumit was also asking like how much detail is in the paper. And I think that's kind of like, if I want to go into a new subject, I look into literature and I want to learn something. And if it's not there, the information, then I can't learn and I can't do the right thing. So I think it is important to include many of the important steps, like what did I sample? How did I prepare the samples? How do I process them analytically? How do I process data? How do I do all of these steps? Because that's all that goes into the data we then show in the paper, as well as make interpretations on it. If that information is often crucially lacking, and I very often get very frustrated because I kind of like want to understand how did they get this number, but I can't, there's no way I can understand this. And I think that needs a shifting of like, this, we spend so much time on it, but then there's so little emphasis on it in a paper. So either we need different formats for publishing methods, or having kind of like, I don't know, blogs or descriptions, I don't know, whatever. But I think that is something which I think needs to shift, because then people can make the right decisions and can get good data. And that's then, I think, important to make interpretations.
I would totally agree with that. And I think one of the dangerous things is not to be aware of the pitfalls. And if you think in terms of thermodynamics, it became quite easy to calculate these isochemical phase diagrams, right? And all of a sudden, people stopped really thinking about what they are doing. And I think this is one of the dangers we are encountering, as more and more diffusion models are available, to really make sure that these diffusion models are actually significant and thought through, and not just a number that's coming out without all the looking at the pitfalls that you might have gone through. I mean, we've seen a lot of warning signs over the past 2 days where people say, pay attention that you know your geometry, you know your problem, and this is the only way you can produce something significant. Because if we start doing a lot, or if we start publishing a lot of, let's say incorrect diffusion models, we are risking to discredit the entire method, if you want, at my personal perception. Any more comments? Yeah, Dan, you would need to unmute yourself.
Yeah, double clicked by accident. Just a very quick one. I'm sorry to say I've got to go because I've actually got a tutorial right now. Very sorry about that. It's a bit of a postponed mapping support one, but I'd just like to thank everybody for letting me come along and have a talk and say it was really stimulating afternoon. So thank you very much for the chance to come and listen.
Thank you, Dan. Thank you, Dan. Great to see you. So, any more questions, comments, suggestions? Tinka.
Yes,
First Tinka, then Bob.
Okay, jumping in on the last comment of being able to reproduce data based on the description of the work done. I think it's important that we in community journals allow for repetition to be published. So when people basically reproduce data on a similar system, let's say, that this should also be publishable to give the credibility to what has been done before, which is a bit also in line with what Ewan showed. Is that how you say your name?
Yeah.
That,
Well done.
yes, because in principle you use better analytical approaches to reproduce data and look at them again. This is not the only way things need to be reproduced, also in experiments, and I think we still lack that to a great extent.
Bob, you had a comment.
Yes, I think the earlier comments about what is publishable in the main papers and what gets hidden away rather in supplementary information. We really need a mechanism for highlighting where there are key bits of methodological stuff in those supplementary things. Maybe the scope for review papers which look specifically in a field over the things which are rather hidden away like that. I think we lack a mechanism to get around that visibility issue.
I think it's a combination of having the a way to present the method in all of its glory, and the awareness that you need that, right? So if all the information would be available in an electronic supplement, then we need to have the awareness to actually look into that as well, and not just take the numbers from or the equation from the abstract.
Well, if you really try to reproduce something, just there are these minimum, these minute little information that are lacking, like how do I touch the bicrystal to put them together? I don't know, it's not really written somewhere. Do I touch it like this, or do I have to touch it like this? I had to find out those things because they're not written anywhere. And the same thing, I just looking at EBSD data, they say they did some data cleaning. I can think of a million ways to clean up the data, and every time I get a unique result. So I need to know exactly how it was done. And it's yes, I agree with what has been said before. It's very frustrating. So.
Schumid.
I just wanted to make two comments. First on this one on data. I mean, this is something that's a lot of people are realizing that have become too focused on the story and not paying or not documenting as well how we are getting there. And so there's actually an initiative now with the Geochemical Society where people are thinking of using the new media that has become available, things like YouTube and so forth, to produce videos where you actually document some of the things. One of the things that came up was that actually some isotope geochemists pointed out that a lot of students don't know how to weigh samples, something as basic and as simple as that. And you cannot go and read that up or look that up somewhere. And that's easy to do these days. And you can have a YouTube video where, you know, somebody's doing it right and telling you how to do that. So we can develop resources in those directions, and then that might help a little bit. And the second thing I wanted to say was related to what Claire was saying about diffusion data. And like you said, Tommy, I mean, I think this will be a continuing thing because as we look closer, we learn and discover new things. So just one example that's happening right now is that we all used to think that, you know, you have crystals and if they have a lot of defects, then things diffuse faster in them. And it's turning out that that's not always the case. And so for thermochronometry, people are finding that helium in quartz, apparently the data you get is because the crystals have, natural crystals have defects, and people have been measuring things in gem quality crystals. So these things with defects actually have slower diffusion than the gem quality stuff that people have been measuring. So that's just something, it'll be a ongoing learning thing on both sides, I think. So I always insist that we need to, do the measurements and go back and apply them and learn from that and go back and do more measurements. So yeah, that's what I wanted to say.
Yeah.
Thomas, can I make a comment?
Yes, of course.
I mean, I'm not exactly at the heart of this community, but sort of as an interesting, sort of interested, slightly outsider, it strikes me that one of the ways forward in which I think would greatly help the community, but also people that are interested in applying it, but are not necessarily sort of career diffusers, if you will, to have something like a community benchmark standard data set that everyone can apply their method to demonstrate what their method does to this benchmark. It's exactly what say the numerical modeling community is very good at. They come together, they have a benchmark data set that everyone should be able to model, whatever their model wants to do, however they want to approach the methodology. They all apply to the benchmark and publish that benchmark for their model to see exactly what they get out. And so everyone can then, first of all, make sure that they get the right sort of ballpark answer so that it's clear that the methodology is robust. People that are new to the community can have a go at the benchmark just to make sure they're up to scratch on how things work. And critically, everyone's different models, and obviously we're seeing a lot of development of new approaches can be applied to the benchmark just to see where the improvements really are, and everyone can, because it's a community data set that everyone knows, you can see exactly what it does. And that might, it's a fairly simple thing for diffusion, I think, to set up. You just invent a synthetic data set and say, we're all going to apply it. And it doesn't take much work to do. And that might be a really good way forward.
Can I just comment there, Thomas?
Which occurred to me yesterday when we were talking about some of the extra things one would like to incorporate in experiments, which are very difficult and time consuming. And that is, we've not mentioned at all the potential for numerical approaches to understanding what will and won't happen in diffusion. And with increasing computing capacity, it isn't there potential there to supplement what one can do in the laboratory?
It's good that you point that out, because the one example that I just mentioned of helium in quartz, they did in fact exactly that. They did some experiments, and then they also did ab initio calculations to demonstrate that the defects were what was causing the difference. So yeah, that's coming in, that's happening, and that's a very powerful direction to go to. So this is, I think, Melissa Tremblay and those people in Chicago and Stanford were doing that.
I think the benchmark idea is very, very good idea. What I would be scared a little bit is, as we are developing these diffusion models and basically finding more and more things we need to add in order to properly describe diffusion in the systems, we would need to shift the benchmarks. And so we would basically have to have some sort of maintenance of the benchmark data sets, continuous one, which someone would really need to put effort in that. So I think the principal idea is the way to go forward. I just see some practical issues, but maybe
I think we have to realize there are several communities in this meeting, and you can't just take an approach tied to people who are solving intracrystalline diffusion and expect to be able to apply it across all the possible problems. I mean, you get different aspects of problems, and if you're working on diffusion and disposal of radioactive waste in groundwater, then you're dealing with different parts of the problem than if you're dealing with the growth rates of igneous crystals. But the core aspects of some of the problems are common. And I think it's important to recognize that there are different aspects of diffusion which some people really need to work with and other people frankly, don't have to worry about. But we need to explore them all and know how they all work, but not expect them to all work exactly the same way. So that if people working on diffusion associated with veins have worked out some methodologies there, then somebody who has been working perhaps on volcanic systems can go and work at plutonic rocks or whatever and find something useful in what the other community has done. So we can't expect everyone to be doing the same thing all the time, but it's really important that we understand what each others are doing so that we can draw on their expertise and their experience when we need to.
Yeah. But on the other hand, it would be good to have basically a set of, or some set of, well, basically principles of diffusion, right?
Oh yeah,
where you can, when you're starting your career as diffusion modeler, can test yourself, can test your first models and see whether you get the same answers. Yeah, before you basically put your add-on to your specific model.
The model should solve the equations correctly.
Exactly. Lucy.
Yeah, this is just a comment of my not only mine, but we were a group of people, like from, I think it was last year, during this anniversary of Mineralogical Society of America, that it would be cool to establish like a international virtual institution kind of, or a platform, and the MSA would be able to host it, where we could put like, as Shumit said, some like a YouTube material for like even not like basic things, how to do some stuff for the students or for people who are trying to use the method for the first time and so on. And this can go also up to a higher up level. So it means that we can put there also like kind of YouTubes, or we can organize webinars and so on for the like cutting edge methods. And also it can be maybe a platform where we could share these kind of like a data sets or something like this for the benchmarking and so on. We advertised it last year several times on Geometamorphism and elsewhere because I don't have the capacity to create it and to maintain it. So we would need some volunteers to do that. But MSA for sure agreed to host such a thing. So if there is somebody in here who would be interested, you can contact me or Sarah Pennington-Dorlan.
I think this really needs to be a community effort.
Yeah, for sure.
Because I think everyone, it's too much for the plate of a single person.
It must be a team of people on different levels. I think that the PhD students or postdocs or so, there must be somebody or a team of people establishing, like starting really, and then adding the material and the webinars and these things can be created on the way.